Tonight, we are settling in for something quietly remarkable. Beneath everything you see and touch, beneath the table, the lamp, the soft weight of your blanket, there may be no solid things at all, only fields, gently humming, stretched across space. Quantum field theory suggests reality is layered, and the deepest layer is stranger than we usually picture. Wherever you are, perhaps tucked under a blanket, perhaps on a late journey home, perhaps in a quiet kitchen with the kettle still warm, it is lovely to have you here. A gentle like and subscribe helps this small, sleepy channel keep drifting along. And tell me, where in the world are you, and what hour has found you tonight? Let us begin softly. Let us simply sit for a moment with the room you are in tonight. Wherever this finds you, hopefully you are warm. Hopefully the lamp beside you is low, or perhaps off entirely, and the only light is whatever screen is keeping you gentle company. Hopefully your breathing has already begun to slow just a little, in that quiet way breathing does when the world finally stops asking anything of it. Notice, if you would like to, the weight of whatever is covering you tonight. A blanket, perhaps, a duvet, a sheet, a coat draped over you on a long, quiet journey. Feel it pressing very softly against your shoulders, your chest, your legs. It is a small reassurance, that small, steady pressure, the way it confirms, without saying anything at all, that the world is here, that you are here, that gravity is doing its old patient work, holding you against the surface of a planet that has been turning in the dark for billions of years without ever once asking you to thank it. Notice the pillow beneath your head, the way it has shaped itself very slightly to the curve of your skull, the faint coolness on one side, the slightly warmer hollow on the other. Notice, if you happen to have one nearby, the cool surface of a glass on the nightstand, the smooth bevel of its rim, the quiet ring it makes when you set it down, the water inside it, perfectly still, holding the dim shape of the room in a small, unbothered way. These things, all of them, are utterly familiar. The blanket is a blanket, the pillow is a pillow, the glass is a glass. You have known them in one form or another for as long as you have known anything. They feel, in the most obvious sense imaginable, solid. They are here. They are not going anywhere. They do not flicker. They do not waver. They do not slip out of your hand when you reach for them. They are the small, comforting furniture of being awake in a body, in a room, in a life. Tonight we are going to think gently about these things, not to disturb them, not to take them apart, not to make them feel any less trustworthy than they have always felt. They will remain exactly as they are. The blanket will still be a blanket when this is over. The glass will still be a glass. You will still be you, settled in your bed or your sofa or your seat by the window, breathing softly, half listening, perhaps already half asleep. Nothing about the night ahead is going to change any of that. I want you to know that, quietly, before we begin. What we are going to do, slowly, over the hours ahead, is sit with a very small, very quiet idea. The idea is this. For about the last 100 years or so, the people whose job it is to think carefully about what the world is made of have very gradually, very patiently, come to a strange and rather lovely conclusion. The conclusion is not that the world is unreal. It is not that nothing is solid. It is not that you are dreaming. The conclusion is, in a way, gentler than that, and also stranger. The conclusion is that when you look closely enough at the blanket, at the glass, at the pillow, at your own warm hand resting on the edge of the duvet, the most accurate description of what you find is no longer a description of small solid objects at all. It is a description of something quieter, something more continuous, something that has been humming away beneath everything you have ever touched without you ever noticing. For most of human history, we have imagined the world as built from little pieces, from small grains, from tiny solid things that, when stacked up in great enough numbers, became larger solid things. A grain of sand, a pebble, a stone, a boulder, a mountain. The picture is so intuitive, so kind to the way our hands and eyes work, that it feels almost impossible to think any other way. The world is made of stuff, and the stuff is made of smaller stuff, and the smaller stuff is made of even smaller stuff. And somewhere down at the bottom of all that smaller and smaller, there must be the smallest possible stuff, and that is what everything else is made of. Tiny solid grains, little indivisible specks, the bedrock of the real. This is a beautiful idea. It is also, quite possibly, the most stubborn idea in the history of human thought. It has been with us, in one form or another, for more than 2,500 years. It survives because it is so closely matched to the way we move through the world. We pick things up, we put them down, we break them, and we count the pieces. Of course the world is made of pieces. Of course it is, grains all the way down. What else could it possibly be? And yet, very slowly, over the course of the 20th century, something began to soften in that old picture, not in a dramatic way, not with a single moment of revelation, not with a sudden announcement that everything we thought we knew was wrong. The softening came in small steps, often delivered with great reluctance by the people doing the work. Physicists, who tend, on the whole, to be rather conservative about reality, who tend to prefer a stable picture of the world to a strange one, kept finding themselves pushed, very gently, towards something they had not asked for. They kept finding that the closer they looked at the small, solid grains they had been promised, the less solid those grains became, the less like little stones, the less like little pebbles, the less like anything that could be held in any kind of hand. What they found instead is the thing we are going to circle very softly all night. They found that the world, at its deepest layer, does not appear to be made of objects at all. It appears to be made of something else, something that does not sit still in the way an object sits still, something that fills space, rather than occupying a tiny patch of it, something that hums in a quiet, steady way throughout the whole of the universe, something that, every so often, gathers itself into a ripple, into a small, localized excitement, and that ripple is what we have been calling, all this time, a particle. I will say that again, very gently, because it is the only sentence in the whole night that really matters, and I would like you to hear it once now, and then forget about it and rest in it, and come back to it whenever you happen to drift up to the surface of listening. The world, at its deepest layer, may not be made of objects. It may be made of something humming, layered and continuous. The things we have always called particles the small grains we expected to find at the bottom of everything appear, on closer inspection, to be ripples in something much larger. Ripples in something that has been here, quietly, all along. Now, I can already feel how that sentence might land. It can sound, said too loudly, like the kind of thing meant to unsettle you. It can sound like a magic trick, a deflation, an attempt to pull the rug out from under the solid world you live in. So let me say, very plainly, that none of that is what is happening. The blanket is still a blanket. The glass is still a glass. The hand resting on the duvet is still a hand. Physics has not taken these things away from you. It has only changed, very slightly, the story it tells about what they are underneath. It has, in a sense, lifted up one corner of the rug very carefully and found that underneath the floor is not made of little stones at all. Underneath the floor there is something quieter, something stranger, something that has been holding the floor up the whole time without ever making a sound. This is the gentle promise of the night. We are going to spend the hours ahead walking slowly around this idea, not running at it, not crashing into it, not pretending that it is more dramatic than it is. The strangeness will come on its own, in its own time, and we will sit with it for a while, and then we will turn back toward the room, toward the lamp, toward the cup of water by the bed, and we will let the strangeness settle quietly into the ordinary again. By the end, if everything goes well, the world will look exactly the same as it does right now, only it will rest very gently on a slightly softer foundation than you thought it did. There is no rush. There is no test at the end. There is no part where the music swells and a great revelation is announced. The whole point of tonight is to let an unusual idea arrive at the slow pace your body actually likes. The pace of breath, the pace of a curtain moving in a soft breeze, the pace of a clock you can hear ticking 3 rooms away. If at any point you find yourself drifting, that is exactly what should happen. The story will still be here when you come back. And if you happen to fall asleep before we reach the end, that is, in some ways, the most generous outcome of all. Sleep is, after all, the only honest response to a long, quiet voice talking about the nature of reality at this hour. Let us come back, for a moment, to your hand. Bring your attention, if you would like, to one of your hands. Perhaps the one that is not holding anything. Perhaps the one resting palm down on the duvet, or curled gently near your face, or lying open beside you. Notice how clearly it feels like a hand. Notice the slight warmth of it, the small weight of it. The way the fingers, even when relaxed, are not quite straight, but curl very softly inward, as hands do when they are not asked to do anything. If you were to look at this hand under a powerful microscope, you would see skin, of course, and below the skin, cells, and below the cells, smaller arrangements of molecules, all very busy, all carrying out their patient, quiet work, and below the molecules, atoms, tiny patterns of atoms, hooked together in long flowing chains, and below the atoms, even smaller things still, electrons, protons, neutrons, the familiar cast of any school textbook. And then, below those, smaller things again, quarks, tiny patient quarks, 3 to a proton, 3 to a neutron, bound up inside the nuclei of every single atom in your hand. This much is fairly well known. This much most of us have heard before. The picture here is still the old picture. Small things made of smaller things made of even smaller things. Grains all the way down. The hand is a careful tower of little Lego bricks stacked very neatly all the way to the bottom. But this is exactly where the softening begins. Because if you ask very gently what those bottommost things are, the little quarks, the lone electrons, the tiny photons that carry light into your eyes, you find that the textbooks, when they are being honest, begin to hesitate. They begin to choose their words more carefully. They stop saying that an electron is a little ball, and they start saying that an electron is something more like an excitation, a disturbance, a small focus stirring in something much wider. The same is said of the quarks and of the photons and of every other small thing that physics has ever managed to look at closely enough. The word particle, it turns out, was always a kind of polite shorthand, a useful word that physicists kept using because it sounded like the thing we already imagined. But the actual thing the word was pointing to, the actual stuff at the bottom of everything, was not, on closer inspection, a tiny grain. It was something else. Something that had a value at every point in space, not just at one tiny location. Something that did not have edges. Something that, in some sense, fills the room you are sitting in right now, fills the air around your face, fills the small space between you and the lamp, fills the inside of the cup on the nightstand, fills the inside of your chest as you breathe. Now, please, do not be alarmed by that. It is a gentle filling. It is not a noise. It is not a crowd. It is not a busy, invisible thing pressing against you. It is quieter than quiet. It is, in the most literal possible way, the soft fabric of the room itself, the soft fabric of all rooms, the soft fabric of everywhere. We do not feel it, because there is no separate elsewhere from which to feel it. It is not pressing against us. It is what we are made of. It is what the blanket is made of. It is what the glass is made of. It is what the air between the glass and your hand is made of. And the slight differences between blanket and glass and hand and air, the differences that make a blanket feel like a blanket and not like a glass, come down to small differences in how this very quiet fabric is humming, here as opposed to there. This is the picture we are walking very slowly toward. We will not arrive there fully tonight, not in the sense of understanding every detail, because there are many details, and many of them are technical, and most of them, frankly, are not necessary for the gentle understanding I would like you to carry with you into sleep. What we will arrive at, if we go slowly enough, is something more important than detail. We will arrive at a kind of soft permission. Permission to look at the blanket and the glass and the hand, and to know somewhere in the back of your mind that beneath their familiar solid surface, something is humming. Something has been humming all along. Something is humming right now, in the place where you are, in the place where I am writing this for you, in the place where every single person listening to this is also lying in their own quiet room, settled in their own quiet way. And that humming, that quiet underlying continuity, has a name. It is called, in the long, careful language of physics, a field. We will spend a great deal of the night with that word. We will turn it over. We will hold it up to the lamplight. We will let it become familiar, in the way unfamiliar words sometimes become familiar over a long evening, slowly, without anyone making a fuss about it. By the end, you will not be afraid of the word field. You will, I hope, find it rather comforting, the way certain old words become comforting once you have spent enough time with them. But before we go anywhere near that word in any serious way, I want to stay here a little longer in the room with you, with the blanket and the pillow and the cool glass and the quiet hand. Because the most important part of any conversation about the nature of reality, in my opinion, is the moment before the conversation begins. The moment where we agree, very softly, that nothing terrible is about to happen, that the ground is not going to fall away, that the world is not going to be revealed as a hoax, that this is, in the end, just a quiet thought being passed gently from one person to another in the dark, late at night. Tonight is one of those moments. The ground is not going to fall away. The world is not going to be revealed as a hoax. You are not going to be asked to give up the blanket, or the pillow, or the glass, or the hand, or any of the other small, ordinary things that make this hour feel like itself. We are only going to lift up, very gently, one corner of the floor, and we are going to look underneath, and what we see there will be quiet and continuous, and a little stranger than we expected, and then we will lower the floor back down, very carefully, and the room will look exactly as it does right now, only with the soft knowledge that beneath everything, something is humming. So let us stay here, in the room, for one more moment. Notice, again, the weight of the blanket, the cool of the glass, the pillow under your head, the slow, steady work of your breath. Notice, if you can, that none of these things needs to change for the night ahead to be true. None of them is in any danger. None of them is going to be diminished by what we learn. They are, all of them, exactly what they appear to be. They are also, at the same time, something quieter and stranger and more continuous than they appear. Both things are true. Both stories are the same story, told at different depths, and we have all evening to wander between them gently in our own time. So let us begin, shall we? Slowly, without any particular hurry, with the blanket where it is, and the glass where it is, and your hand where it is, and the lamp low, and the night long, and the small humming layer of reality, whatever it turns out to be, waiting patiently underneath us, as it has been waiting all along. So let us turn now, very gently, to the long story of how we got here, not as a lecture, not as a list of dates, but as a slow walk through a quiet corridor of human thinking, with the lamps lit low and the conversation kept soft. The story is, in a way, the story of how a single very old idea, an idea that almost everyone has held at one point or another, was slowly, patiently, almost reluctantly let go of. The old idea was that the world is made of small, solid grains. The new idea, the one we are walking toward, is that it might not be, but we are not in any rush to arrive. The corridor is long, and there are many gentle doorways to look into on the way. Let us begin then with a person standing on a beach, or perhaps more accurately, with a person walking along the edge of a quiet harbour, somewhere on the coast of what is now Greece, more than 2,400 years ago. His name was Democritus, and he was, by all accounts, a rather cheerful man. There is a long tradition of describing him as the laughing philosopher, the one who walked through the troubles of the world with a small, amused smile, as if everything could be made bearable by thinking about it carefully enough. We know almost nothing about him, really. Most of what he wrote has been lost. What survives comes to us through other writers, quoting him, paraphrasing him, occasionally arguing with him. But the idea he is remembered for is the one we are interested in tonight. Democritus believed, very firmly, that if you took anything in the world, anything at all, a stone, a piece of bread, a leaf, a thread of wool, and you broke it in half, and then broke the half in half again, and then again and again, you would eventually arrive at something that could not be broken any further, some tiny final piece, some smallest possible grain. And he gave this idea a name. He called these final pieces atomos, a Greek word that means, very simply, uncuttable. The uncuttable things, the pieces that go all the way down. It is, I think, a rather lovely image. A man on a beach, picking up a handful of sand and quietly imagining that even each grain of sand, if you only had small enough fingers, could be broken into smaller grains, and those into smaller still, until at last you arrived at the true grains, the uncuttable ones, the bedrock of the world. He did not have any way of testing this idea. He could not see atoms. He could not measure them. He could only think about them and decide, in the privacy of his own mind, that they must exist, because the alternative, that the world was infinitely divisible, was the kind of idea that made his head feel uncomfortable. Atoms felt like a quieter conclusion, so he chose them. For more than 2,000 years after Democritus, his idea drifted in and out of fashion. Sometimes it was taken seriously, sometimes it was dismissed entirely. The great thinkers of the medieval period mostly preferred a different picture, in which everything was made of 4 elements, earth and water and air and fire, mixed in different proportions. The idea of tiny indivisible grains was, for long stretches of history, regarded as a slightly eccentric old Greek opinion, the sort of thing a clever person might think about on a slow afternoon, but not the sort of thing on which one would base a serious description of the world. And yet the idea would not quite go away. It kept coming back, very softly, in the writing of various philosophers and natural scientists, century after century, the way certain small, persistent thoughts keep coming back when you are trying to fall asleep. Eventually, in the early 19th century, in the quiet north of England, a rather shy schoolteacher named John Dalton picked the idea up again and gave it a kind of practical shape it had never quite had before. Dalton was, in many ways, exactly the sort of man you would want to spend an evening with if you were trying to learn something carefully. He was patient. He kept records. He had an enormous interest in the weather, which he tracked daily for most of his life in a series of small, careful notebooks. He was colorblind, in fact, and he wrote a thoughtful paper about it, one of the first such papers anyone had written. He moved through the world quietly, doing his small, careful experiments in a small, careful way. And he came to the conclusion that the various substances of chemistry, the things that combine and recombine in the test tubes of a laboratory, behaved in a way that made the most sense if you imagined each chemical element as being made of its own particular type of tiny grain. Hydrogen grains, oxygen grains, carbon grains, each different from the others, each combining with the others in fixed, simple ratios. This was, in its way, the moment when the old Greek idea began its second life. Dalton did not call his grains atomos exactly, but the connection was clear and the word atom came forward to do the work. Suddenly, the idea was no longer just a philosophical preference. It was a practical tool. It explained very neatly why a certain weight of hydrogen always combined with a certain weight of oxygen to make a certain weight of water. It explained why some substances could be broken down into others and some could not. It explained, in short, a great many things in chemistry, and it explained them so well that, by the middle of the 19th century, atoms had quietly become part of the working furniture of science, and the picture, in those days, was very satisfying. Atoms were imagined as small solid spheres, tiny indivisible little balls. Different kinds of atoms had different sizes, different weights, perhaps different colors. In the schematic drawings of the time, they were, in essence, very small marbles. The world, it seemed, really was made of grains, just as Democritus had said, and now we had finally found them, and they were just as well behaved as anyone could have hoped. They were like miniature stones. They did not move when nothing pushed them. They did not change. They sat patiently in molecules, the way good furniture sits patiently in a room, doing exactly what was expected of them and no more. It is hard, looking back, not to feel a small affectionate amusement at this picture. There is something so neat about it, so tidy, so reassuring. The world made of marbles. The marbles made of nothing smaller, because they were the smallest possible thing. The whole long history of human curiosity finally settled in the form of very small balls. But the 19th century, even as it embraced this picture, was already beginning to find loose threads in it, quiet little inconsistencies, small things that did not quite fit. The behavior of certain glowing gases in certain glass tubes when an electric current was passed through them, the strange patterns of light that came out of heated metals, the puzzling way that hot objects glowed first red, then orange, then yellow, then white as they grew hotter, without doing any of the things the existing theories said they should do. None of these mysteries seemed particularly serious at first. They were the kind of small, loose threads that a careful chemist or physicist might notice, pull at gently, and either tuck back in or expect to be explained, eventually, by someone with more time. Then, very near the end of the 19th century, the threads started to come loose in earnest. In 1897, a thoughtful and slightly distracted man named J.J. Thomson, working in a laboratory in Cambridge, was studying one of those mysterious glass tubes, the kind with a small electric current running through it. He found, to his considerable surprise, that the glow inside the tube seemed to be made of something that responded to magnets, something that had a tiny negative charge, something much smaller than any atom anyone had ever imagined. He had, without quite meaning to, found the first thing smaller than an atom. He called it, with charming simplicity, a corpuscle, though the name electron, suggested by someone else, eventually took its place. The atom, the supposedly uncuttable, was, on closer inspection, made of something else. The Greek word atomos had, it turned out, been a slight overstatement. The atoms of chemistry were not the final grains after all. They were larger things, with smaller things inside them. For a moment, this was not such a great upheaval. The picture simply became slightly more detailed. Now the atom was a small, solid sphere with tiny electrons embedded in it, like raisins in a pudding. That was, in fact, the picture Thomson himself preferred. The plum pudding model, as it was rather fondly called. The atom as a small, soft ball, dotted with smaller pieces. Still very nearly a marble, still very nearly a grain. The old picture only a little gentler around the edges. But within just over a decade, even that picture was beginning to look quaint. In 1909, working in Manchester, a New Zealander named Ernest Rutherford, along with two younger colleagues named Hans Geiger and Ernest Marsden, performed a small, careful experiment that would change everything. They took a very thin sheet of gold foil, no thicker than a few thousand atoms, and they fired tiny positively charged particles at it, and they watched very carefully to see what happened. What they expected was a small, soft scattering. The little particles should have passed through the gold foil with only the gentlest of deflections, as if pushing through a thin mist. That was what Thomson's pudding model predicted. A thin haze of charge, easily traversed. What they found was, in Rutherford's later words, almost the most incredible event that had ever happened to him in his life. Most of the particles did pass through with very little deflection, as expected. But every so often, one of them came bouncing back, straight back, as if it had hit something very small and very hard. The image he reached for, when he tried to describe it later, was that it was as if you had fired a great shell at a piece of tissue paper, and the shell had come back and hit you. What this meant, after careful thought, was that the atom was not a soft pudding at all. The atom was mostly empty space. Almost all of its mass and all of its positive charge was concentrated in a tiny, tiny region at its center, which Rutherford called the nucleus. The electrons were not embedded in a soft ball. They were drifting somewhere out beyond the nucleus, in a great deal of nothing. The atom, on closer inspection, was less like a marble and more like a very small sun, with a few very small distant planets around it, separated from the center by what was, in proportion, a frankly absurd amount of emptiness. Now, this was a strange thing to learn. If you press your hand against a table, the table feels solid. You do not feel as if your hand is touching something mostly made of empty space. And yet, by 1911, the best understanding of atoms said exactly that. The solid table and the solid hand were both, on closer inspection, almost entirely empty. The little nuclei were very small. The electrons were even smaller. Between them, in the volume occupied by each atom, there was, by ordinary standards, a great deal of nothing. This was the first quiet hint that solidity was not quite what it seemed. The table did not feel empty. The hand did not feel empty. And yet, in the most literal sense one could give the word, both of them were. Whatever it was that made the table solid was not the simple presence of matter filling the space. It was something else. Something to do with how the electrons of one atom related to the electrons of another. Something to do with the way certain small things refused to pass through certain other small things, even when there was, ostensibly, plenty of room. We will come back to this. For now, simply notice it. The first crack in the marble, the first soft suggestion that the old picture was not going to survive entirely intact. And then, in parallel with all of this, in a different corner of physics, something even stranger was happening. While people like Rutherford were learning to take atoms apart, other people were learning, very reluctantly, that light itself was not behaving the way it should. For most of the 19th century, light had been understood beautifully and convincingly as a wave, a smooth, continuous wave traveling through space, in much the same way that ripples travel across the surface of a pond. The work of James Clerk Maxwell in particular had given physics a wonderful set of equations describing exactly how those waves of light moved, how they interacted with electric and magnetic fields, how they carried energy from a hot lamp to a cool eye across the empty distance of a quiet room. By the end of the 19th century, this picture of light as a wave was so well established that some physicists were beginning to worry, slightly, that there was nothing important left to discover. But there were small problems, stubborn small problems. One of them, in particular, would not go away. It had to do with the way a hot object, like a piece of iron in a fire, glowed. The standard wave theory of light said that such an object should give off enormous amounts of energy at very short wavelengths, far more than it actually did. The discrepancy was severe. The mathematics simply did not agree with the world. Something was wrong somewhere, and no one could quite see where. In 1900, a thoughtful and rather careful man in Berlin named Max Planck made a small, reluctant suggestion. He proposed, as a kind of mathematical trick, that the hot object did not give off its light in a smooth, continuous flow, but in small, discrete packets, tiny, indivisible portions of energy. He called these portions quanta, from the Latin for how much. He did not, at the time, particularly believe in them. He thought of them as a convenient bookkeeping device, a way of making the equations come out right. He hoped, in fact, that someone would eventually find a more elegant explanation that did not require such small, uncomfortable jumps. But the trick worked. The mathematics finally agreed with the world, and no more elegant explanation was forthcoming. The little packets of energy stubbornly refused to go away. 5 years later, in 1905, working in a patent office in Bern, a young man named Albert Einstein took Planck's reluctant trick and quietly, gently, turned it into a serious claim about the nature of light itself. He suggested that light really was made of these little packets, these quanta of energy, and that this was the only way to understand a small, puzzling experiment in which light shone on a piece of metal could knock electrons out of it, but only if the color of the light was right, regardless of how bright it was. The behavior made no sense if light was a smooth wave. It made beautiful sense if light came in small, discrete portions, each carrying a fixed amount of energy depending on its color. These small portions, eventually, would be called photons, and by suggesting they were real, Einstein had quietly, almost apologetically, introduced one of the strangest ideas in the history of physics. Light, which everyone had agreed was a wave, was also, in some way, a little grain. Not a marble, exactly. Not a stone. Something else. Something that behaved like a wave most of the time, and like a grain the rest of the time, and that did not seem to mind doing both, even though it made very little sense to anyone trying to picture it. Then, In 1913, a soft-spoken Danish physicist named Niels Bohr took all of this and made a further leap. He proposed, with very little justification at the time, that the electrons drifting around the nucleus of an atom were not free to move in any orbit they pleased. They were, instead, restricted to certain particular orbits, certain quiet, permitted distances from the nucleus. They could be in one orbit or in another, but not in between. To move from one to the other, they had to absorb or release a single small packet of light with exactly the right amount of energy for the jump. This was, in many ways, the moment when the old picture of the world finally began to crack open in a serious way. Because what Bohr was saying, very softly, was that the inside of an atom was not behaving the way ordinary things behave. Ordinary things, larger things, can sit anywhere they like. A pebble on a table can be in the middle of the table or near the edge or any of the infinite positions in between, but an electron inside an atom, according to Bohr, could not. It had to be in one of a small set of allowed states, and to move between them it had to absorb or release a precise small portion of light. The atom, on the inside, was nothing like a tiny solar system after all. It was something stranger. It was something quantized. It moved in small, careful steps. By the time the 1920s arrived, the old picture of the world as a great collection of tiny, solid marbles was, very quietly, in deep trouble. Light was acting like both a wave and a grain. Electrons, when looked at carefully, were behaving in the same uncomfortable double way, sometimes producing patterns that only made sense if they too were waves, sometimes acting like small localized things. The hard little marbles of the 19th century were beginning to feel more and more like rough approximations of something else. Something that did not quite want to be either a wave or a grain, but kept being described as one or the other, depending on what experiment was being done. By the late 1920s, in the patient minds of people like Werner Heisenberg, Erwin Schrödinger and Paul Dirac, a new picture was beginning to take shape. A picture in which the word particle, used so confidently for so long, was beginning to feel, very gently, like a polite fiction. Not a lie, exactly, not a mistake, just a word that no longer quite fit the things it was supposed to describe. The little grains at the bottom of the world were not, on closer inspection, grains at all. They were something else, something that filled space rather than occupying a small piece of it, something that hummed, very quietly, all the way through. We were, by the close of that strange decade, no longer really walking through a world of atoms in the old sense. We were walking, without yet quite realizing it, into a world of something much softer, much more continuous, much stranger. A world in which what we had been calling particles were beginning to look less like little stones and more like ripples in something larger, something patient, something that had been waiting under the floor of physics all along, very quietly, for someone to lift the corner of the rug. And that something, that quiet underlying continuity, the soft fabric that was about to take the place of the old, hard little marbles, is what we will turn to next. Slowly, of course, without any particular hurry, with the lamp still low and the night still long, and the gentle suspicion already settling in, very softly, that the world is not quite made of what we thought it was. So let us turn now, very gently, to the word that will quietly hold the rest of the night together. The word is field. It is a small word, an unassuming word, the kind of word you might use to talk about a meadow or a stretch of grass behind a house. In physics, it has a slightly different meaning, but the everyday flavor of it is not entirely lost. A field in the physics sense is still something stretched out, still something spread across space, still something that does not have a single small location, the way a stone has a single small location, but instead has a kind of quiet presence everywhere. We are going to spend a long time with this word tonight. We will not rush through it. We will not try to define it cleanly in a single sentence and then move on. We will build it up, instead, from the kind of small everyday experiences that you have already had 1,000 times without thinking about them, because that is, in the end, the only honest way to learn what a field is. The mathematics is precise and rather lovely, but the mathematics is not necessary for understanding. The understanding, the gentle intuitive feeling for the thing, comes from noticing a few quiet, ordinary moments in your own life and seeing, very slowly, that they have been telling you what a field is all along. So let us begin in a kitchen. Imagine, if you would like, that you are standing in a quiet kitchen, late in the evening, the kind of kitchen with only one small lamp lit, the kind of kitchen that smells faintly of bread, or of soap, or of the particular smell that kitchens have when they have been used kindly for a long time. On the counter, there is a kettle. It is one of those kettles, perhaps, that sits on a stove, or perhaps an electric one with a soft amber light on the side. It has just finished boiling. The water inside it is hot. Steam is rising very gently from the spout. The metal of the kettle itself is warm, much warmer than the air around it. Now, without moving any closer, without putting your hand on the kettle, simply notice what is happening in the kitchen. The warmth of the kettle is not staying inside the kettle. It is very softly spreading. It is filling the air around it. It is making the space directly above the kettle a little warmer than the space across the room. It is making your face, if you stand a foot or two away, feel a faint, comforting glow on the skin. Step back and the warmth fades. Step closer and it grows. There is no single line where the warmth begins. There is, instead, a kind of soft slope, a gradient, a quiet variation from very warm right at the kettle to barely warm a few feet away to ordinary room temperature near the door. This, in its simplest possible form, is a field. The temperature of the air, as it varies smoothly through the kitchen, is a field. There is a value, a particular temperature, at every single point in the room. Right next to the kettle, the value is high. Across the room, the value is lower. In the corner by the window, on a cold night, the value is lower still. The temperature does not exist at one location only. It exists, in some sense, everywhere in the room. You can walk through it. You can pass your hand through it. You can stand very still in one part of it and feel exactly what it is doing at that point. This is what physicists mean, in the most basic sense, when they say the word field. A field is a quantity that has a value at every point in space. That is the whole of the definition. A field is not a thing you can pick up, the way you can pick up the kettle. It is not a thing you can put down, the way you can put down a cup. It is more like a property of the room itself. varying smoothly from place to place. It is, in a quiet way, a description of what space is doing at each location. Notice, please, how unalarming this is. Temperature as a field is something you have felt your whole life. Every time you walked from a warm room into a cool hallway, every time you stood near a radiator on a winter evening, every time you stepped out of a sunny patch into the shade of a tree, you were moving through a temperature field. You were experiencing, with the soft senses of your own skin, the way a value can vary smoothly from one point in space to another. You did not need any mathematics to know this. You did not need any equations. You simply noticed, with your body, that the world was a little warmer here and a little cooler there, and you adjusted your position accordingly, the way any sensible person does. Let us stay with this for a moment, because it is the foundation of everything that follows. The kitchen with the kettle, the slope of warm air rising from the spout, the way the warmth thins out as you walk toward the far end of the room. This is a field. This is the gentle texture of what a field is. A continuous variation, spread across space, with a value at every point, not concentrated in any one place, but distributed softly throughout the whole region. Now, before we go further, let us add a second example. Because temperature is helpful, but it is also rather familiar, and sometimes the familiar things sneak past us without quite registering. Let us think then about a magnet. Imagine, if you would like, a small magnet, the kind of small magnet that holds a piece of paper to the front of a refrigerator, a modest little thing, perhaps shaped like a flat disc, perhaps the shape of an old letter you once received. Pick it up gently in your imagination and hold it close to a paperclip lying on a table. Do not let them touch. Hold the magnet, perhaps half an inch above the paperclip, and watch what happens. The paperclip moves. It does not move because anything has touched it. It does not move because the air around it has done anything dramatic. It moves because the magnet, even at a distance, is exerting a pull on it. The pull weakens if you raise the magnet higher. It strengthens if you lower the magnet closer. At a certain point, the paperclip jumps the small remaining gap and clings to the magnet with a small soft click. This is, again, a field. The magnetic field of the small magnet exists everywhere around it. Right at the surface of the magnet, the field is strong. A few inches away, it is weaker. A few feet away, it has faded to nearly nothing. But it does not have a single location. It is not sitting inside the magnet alone. It is stretched out around the magnet, with a value at every point in the surrounding space, varying smoothly from strong at the center to gentle at the edges, to essentially zero by the time you reach the other side of the room. And the paperclip, lying on the table, was sitting in this field the whole time. It was not aware of it, of course. It was just a paperclip. But the field was there, all the same. And when you brought the magnet close enough, the value of the field at the location of the paperclip became strong enough to actually move the small piece of metal, to pick it up and lift it gently from the surface of the table. This was, for a very long time in the history of human thought, a deeply puzzling thing. The magnet was not touching the paperclip. There was no string between them, no thread, no visible push, and yet the magnet was doing something. It was reaching, somehow, across the small gap of empty space and acting on the paperclip. The same with gravity. The Earth, 93 million miles from the Sun, was being held in its orbit by something the Sun was doing across that enormous distance. There was nothing visible connecting them. There was, ostensibly, only emptiness in between. And yet, something was happening. Something was being passed across the gap. For a long time, this kind of thing was called action at a distance. It was, in essence, a confession, a way of saying, we do not know how this works, we only know that it does. The magnet acts on the paperclip across empty space. The Earth acts on the Moon across empty space. We do not know why. We do not know what is in the gap. We only know that things at one location somehow influence things at another, even when there appears to be nothing between them. This was the picture that physics inherited from Isaac Newton, who had written, with extraordinary care, the equations of gravity in the 1680s, and who had openly admitted that he had no idea what gravity actually was. He could describe how it behaved. He could predict the orbits of planets to an astonishing precision. But the question of how the Sun and the Earth were managing to influence each other across all that empty space was, for him, a question he chose not to answer. He simply wrote down the equations and let other people worry about the deeper meaning. For about 150 years after Newton, the question of action at a distance was largely set aside. It was treated as a kind of dignified mystery. The equations worked, that was enough. Whether there was actually something in the space between objects, doing the work of passing the influence across, was not a question many people felt was worth asking. And then, in the early 19th century, in London, a quietly remarkable man named Michael Faraday began to wonder about it. Faraday is, in many ways, one of the most lovable figures in the history of science. He had almost no formal education. He had started life as a bookbinder's apprentice and had taught himself an enormous amount of physics and chemistry by reading the books he was bound to bind. He had a gift, an absolutely extraordinary gift, for imagining what was happening in a piece of equipment, in a coil of wire, in the small invisible space around a magnet. He could not do the mathematics that his contemporaries were doing, the high abstract equations of the universities. He thought, instead, in pictures, in small mental images of how forces flowed and lines stretched and patterns curved through space. When Faraday looked at a magnet, he did not see an object that mysteriously influenced other objects across empty space. He saw, in his imagination, lines. Lines of magnetic force, stretching out from the magnet, curving through the air around it, reaching across to other magnets, to pieces of iron, to wires through which currents were flowing. These lines, for Faraday, were not abstract bookkeeping devices. They were real. They were, in his mind, the physical reality of the magnet, just as much as the metal of the magnet itself. He even managed to show them in a rather charming way. If you take a magnet and put a piece of paper over it, and then sprinkle iron filings, very fine little flakes of iron, onto the paper, the filings line themselves up along these curved patterns. They trace, in tiny dotted lines, the shape of the magnetic field around the magnet. The pattern is not invented by the filings. It was always there. The filings simply, very obediently, show you where the field is and how it is oriented. This was an enormous shift, although Faraday did not quite have the words for how big it was. He was suggesting that the space around a magnet was not empty at all. The space was full of something real, something that, although invisible, was as present as the magnet itself. The magnet did not act on the paperclip across empty space. The magnet established a field in the space around it, and the paperclip, sitting in that field, responded to the value of the field at its own location. A few decades later, in Scotland, a man named James Clerk Maxwell took Faraday's pictures and gave them, very carefully, a precise mathematical form. Maxwell is one of those figures it is hard not to admire, partly because of what he did, and partly because of how kind everyone seems to have found him. He was thoughtful, modest, and deeply curious. He worked patiently, often in poor health, and he never seemed to take his own genius particularly seriously. He simply did the work. What Maxwell did between roughly 1855 and 1865 was to write down a set of equations that described, with extraordinary completeness, the behavior of electric and magnetic fields. 4 equations, in their final form, 4 small equations. Each of them a description of how the electric field and the magnetic field varied through space and time, and how they were related to charges and currents and to each other. These equations did several remarkable things. The first was that they took Faraday's intuitive pictures and made them mathematically exact. The lines of force that Faraday had drawn became, in Maxwell's hands, precise descriptions of vector fields, of arrows of strength and direction at every point in space. The second was that they unified 2 things that had previously been thought of as separate. Electricity and magnetism, before Maxwell, had been treated as related but distinct phenomena. After Maxwell, they were 2 faces of a single thing. The electromagnetic field stretched throughout all of space, capable of varying and oscillating and carrying energy from place to place. And the third thing, the one that astonished even Maxwell, was that the equations contained, hidden within them, a small, unexpected prediction. They said that a disturbance in the electromagnetic field, if you wiggled the field somehow, would propagate outward through space as a wave. And when Maxwell calculated the speed at which this wave should travel, the number that came out of his equations was, to his immense surprise, almost exactly the known speed of light. Light, it turned out, was a ripple in the electromagnetic field, the same field that surrounded magnets and carried electric currents and pulled paper clips across kitchen tables. Light was not a separate substance traveling through some other medium. It was a wave in the very field that pervaded all of space. The faint glow of a candle on the other side of the room was a small oscillation of the electromagnetic field, propagating gently through the air, reaching your eye, where it caused other small oscillations in the field, which your retina then patiently translated into the sensation of warm yellow light. This was a stunning, deeply quiet realization. It changed, almost overnight, what the world was made of. Before Maxwell, light had been a mystery, and magnetism had been a mystery, and electricity had been a mystery. 3 separate mysteries vaguely related to one another. After Maxwell, they were all one thing, one field, one quiet, continuous presence. filling the room you are sitting in, filling the air between your face and the lamp, filling the empty space between the earth and the sun, filling the vastness between galaxies. The same field, everywhere, always varying, always capable of carrying ripples, always quietly there. And this is the picture I would like you to sit with for a moment. The picture of a field stretched across all of space with a value at every point, capable of being weaker here and stronger there, capable of oscillating, capable of carrying energy from one place to another, capable of doing all the work that we had previously thought of as action at a distance. The sun is not reaching across empty space to warm your face on a summer afternoon. The sun is a very busy region of the electromagnetic field, vibrating energetically, and those vibrations travel outward as light, as ripples in the field, until they reach your face and warm the skin gently. The kitchen with the kettle, the warmth spreading through the room, the temperature varying smoothly from the hot spout of the kettle to the cool corner of the window. That was a field. The small magnet held above the paperclip, the invisible pull reaching across the small gap of empty space. That was a field. The light from the lamp by your bed, falling softly on the cover of the book you have set down. That, too, is a field, quietly oscillating, traveling at 300,000 kilometers per second, reaching your eye in less time than it takes to think about it. A field is not a thing. It is not a cup. It is not a stone. It is not a small grain. It does not have edges. It does not occupy a small region. It is, instead, a kind of soft presence stretched across the whole of space, with a value at every point, varying smoothly, capable of being still and capable of being lively, capable of carrying influence and energy and information from one place to another without ever having to touch anything. By the end of the 19th century, the physics community had begun, very gradually, to take this idea seriously. Fields were no longer just a clever way of picturing electric and magnetic forces. They were beginning to feel like part of the actual furniture of reality. The world was a place in which things existed, and around those things, fields existed too, stretched out, continuous, quietly doing the work of nature. But the deeper turn was still ahead, because the field idea, as it stood in Maxwell's day, was still classical. It was still continuous in the old, smooth sense. The fields could carry waves of any size, any energy, any wavelength, with no restrictions and no surprises. They were elegant, beautiful, well-behaved. They were, in essence, a refinement of the old picture, not a replacement of it. What the 20th century was about to do, very slowly, was to take this lovely classical idea of a field, the idea Faraday had imagined and Maxwell had perfected, and merge it with the strange new quantum behavior that had been showing up in atoms and in light, and in the small, uncomfortable corners of physics that we walked through together earlier. The result of that merging would be something quite different. Something stranger and softer and stranger still. Something in which the field itself would begin to come in small, careful packets. Something in which the ripples in the field would no longer be smooth at every scale, but would, when you looked very closely, behave like little localized things, like small grains of disturbance, like the very particles that the older physics had assumed to be the bedrock of reality. But that turn is for the next part of the night. For now, Simply sit with the gentle idea of a field, the warmth in the kitchen, the pull of the magnet, the light from the lamp, the quiet, continuous presence stretched across the whole of space, with a value at every point, soft, varying, always there. That, in its plain, ordinary form, is what a field is, and that, in some sense, we are still walking toward, is what the world appears to be made of, all the way down, beneath the blanket, beneath the glass, beneath the warm hand resting quietly on the edge of the bed. So let us turn now to the part of the night where the two old pictures, the picture of small grains and the picture of soft, continuous fields, finally meet. They meet quietly. They meet patiently. They meet in the work of a few thoughtful people who, in the 1920s, sat with their pencils and their papers and tried to make sense of a world that was no longer behaving the way it was supposed to. And out of that meeting, very slowly, a new picture emerged. A picture in which the particles that had haunted the imagination of physics for so long turned out to be, on closer inspection, something rather different. Not little stones, not little marbles, but small, careful ripples in something much larger. I want to come to this idea slowly, because it is the central idea of the whole night, and I would like it to arrive gently rather than all at once. So let us begin, again, in the most ordinary possible way, by thinking about water. Imagine a pond, a small quiet pond on a still evening, the kind of pond you might find at the edge of a garden or in the corner of a park late at night when no one is around. The surface of the water is perfectly smooth. There is no wind. There are no insects skating across it. The pond is, for this small moment, doing absolutely nothing. It is just sitting there, holding the soft shape of the trees and the sky in its quiet mirror. Now, in your imagination, drop something into the pond. A pebble, perhaps, a single small pebble, falling once into the center of the still surface. You know what happens next. A small ripple forms at the place where the pebble entered, and then another ripple, slightly larger, just outside the first, and the ripples spread outward in soft concentric rings, gradually weakening until the pond returns, after a few moments, to its earlier stillness. Watch the ripple for a moment in your mind. Notice what it actually is. The ripple is not a separate thing from the pond. It is not a little object that arrived in the water and is now traveling across it. The ripple is the pond. The pond, in that one small region, is rising and falling slightly. The water itself is doing the rippling. There is no extra substance involved. The pond is everywhere. The ripple is what the pond happens to be doing in a particular small region. And as the ripple moves outward, what is moving is not really any water from one place to another, but rather a pattern of movement passed from one part of the pond to the next. This is, with a few important softenings, the picture we are going to walk toward tonight. The picture of a particle as a ripple, not a little object that is somehow placed in space, like a marble dropped onto a table, but a small, localized disturbance in something much larger, something that fills space, something that was already there before the ripple appeared and will still be there long after the ripple has faded. A particle in this picture is a small region of activity in a much wider, quiet presence. It is what the field does locally when it is excited. It is, in the gentlest possible sense, a small, careful trembling of something that was, until that moment, perfectly still. Now, before we go further, I want to acknowledge very softly that this metaphor has limits. Every metaphor does. A pond is a two-dimensional surface, more or less. A field, in the physics sense, fills three-dimensional space, sometimes more. A pond is made of water, which is itself made of molecules, which are themselves made of other things. A field, at the deepest layer, is not made of any smaller thing that we know of. The pond also has a clear edge. You can stand at the side of it and look out at the limits of the water. A field in the physics sense has no edge. It stretches across the whole of space. There is nowhere outside it. There is nowhere it stops. So please hold the image of the pond gently. Use it for the soft, instinctive sense it gives you of how a ripple can be a feature of something larger, of how a small local disturbance can be part of something continuous and wide. But do not insist on the image too firmly. We will set it down eventually and pick up other images, and none of them will be quite right, and that is all right. The thing itself, the field, is not really like any one thing in ordinary experience. It is itself, and the metaphors only ever point softly toward it. With that small acknowledgement in place, let us turn to the people who began, in the 1920s, to take this picture seriously. The story does not really have a single starting point. It has, instead, a soft accumulation of small steps taken by several people in different places, often without quite realizing what they were collectively doing. But if there is one moment that physicists today look back on as the gentle hinge of the whole transformation, it is a paper written by a young man named Paul Dirac in early 1927. While he was working in Copenhagen at the Institute of Niels Bohr, Dirac was, by the descriptions of those who knew him, an extraordinarily quiet person. He spoke very little. He did not waste words. He had an almost mathematical sense of when to be silent. There are many stories told about his quietness, some of them probably exaggerated, but the general picture is of a man who thought slowly, deeply, and carefully, and who said only what was necessary, and only when it was necessary. In 1927, Dirac was thinking about light. He was thinking, in particular, about the strange double behavior of light that we walked through earlier in the night. The behavior in which light sometimes acted like a smooth wave, beautifully described by Maxwell's equations, and sometimes acted like a small packet of energy, beautifully described by Planck and Einstein. These two pictures had been sitting next to each other for 2 decades, doing different jobs in different contexts, never quite fitting together. The wave picture worked beautifully for some experiments. The particle picture worked beautifully for others. No one had managed to put them into a single consistent framework. They were 2 parallel descriptions, both partly right, and physics had been gently waiting for someone to find a way to unify them. What Dirac did, in his quiet way, was to take the existing classical theory of the electromagnetic field, the field of Faraday and Maxwell, and apply to it the rules of quantum mechanics that had recently been worked out by Heisenberg, Schrödinger, and others. Up to that point, quantum mechanics had been used to describe the behavior of small things like electrons inside atoms. It had not yet been applied to fields. Dirac took the leap. He treated the electromagnetic field itself as a quantum mechanical object. He asked what would happen if you applied the small, careful rules of quantization, the same rules that had made electron orbits in atoms behave in their stepwise way, to the field that filled all of space. The answer that came back was, in its own way, breathtaking. When you quantized the electromagnetic field, the field itself stayed continuous, stretched across space as before, but its energy was no longer free to take any value at all. The field could only oscillate at any particular frequency in small, discrete portions. The smallest possible oscillation of the field at any given frequency carried a specific, small amount of energy. Larger oscillations carried 2 such portions, or 3, or 4. The field, in essence, could only ripple in small, careful units. And these small, careful units, these smallest possible oscillations of the electromagnetic field, were what people had been calling photons. The little packets of light that Einstein had reluctantly proposed in 1905, the small, discrete portions of light that knocked electrons out of metals, the tiny, granular things that everyone had been struggling to picture, were not, in this new view, little balls of energy traveling through empty space. They were the simplest, smallest, quietest possible ripples of the electromagnetic field. They were what the field does when it is doing the least possible amount of something. This was, in a way, the moment when the old word particle began to soften into something gentler, because a photon, in Dirac's new picture, was not really an object at all. It was an event. It was a small excitation of a field. The field was the deeper thing, the more fundamental thing. The photon was what happened, locally, when the field rippled in its smallest possible way. For a while, this picture was applied only to light. The electromagnetic field, Maxwell's field, was the one that had been quantized. The little oscillations of that field were photons. That much was clear. But almost immediately, a quiet question began to form in the minds of those who were working on these things. If the electromagnetic field could be quantized, and its small ripples turned out to be photons, then what about the other particles? What about electrons? What about the small things that had been the subject of quantum mechanics in the first place? Here, the story becomes, very gently, almost inevitable, because if light, which had been thought of as a wave, turned out also to be a kind of particle when the underlying field was quantized, then perhaps electrons, which had been thought of as particles, were also waves of some kind. And in fact, only a few years before Dirac's 1927 paper, a thoughtful Frenchman named Louis de Broglie had suggested exactly that. He had proposed in his doctoral thesis that every particle should have a wave associated with it, with a wavelength determined by its momentum. The idea had seemed strange at first, but a few small experiments had quickly confirmed it. Electrons, when sent through certain crystals, produced the same kind of patterns as waves did. They diffracted. They interfered. They behaved in every observable way, like waves, even though everyone had been calling them particles for 30 years. So the question began to form: if electrons behave like waves, and if the photons we used to think of as particles turned out to be ripples in the electromagnetic field, Then, perhaps, the electrons we used to think of as particles were also ripples in some other field, a field for electrons. A patient electron field stretched across all of space, just like the electromagnetic field, but humming with a different rhythm, capable of rippling in its own particular way. And that, it turned out, was exactly the right thought. In the years following Dirac's 1927 paper, this idea was developed gradually by Dirac himself and by others, including Pascual Jordan and Wolfgang Pauli, into a broader framework. In this framework, every kind of particle was associated with its own field. Electrons came from the electron field. Photons came from the electromagnetic field. And later, as more kinds of particles were discovered, each was associated with its own quiet, stretched out, underlying field. The implication, gently and slowly, was enormous. It meant that the world was not, at the deepest level, made of particles at all. It was made of fields. Particles were not the fundamental things. They were small ripples in the fundamental things. The fundamental things were the fields themselves, soft, continuous, everywhere, humming away through every cubic centimeter of space, in your kitchen, in your bedroom, in the air between your face and the lamp. Let me say that again, very softly, because it is the heart of everything we are walking toward tonight. The world, at its deepest layer, is not made of particles, it is made of fields. Particles are the smallest possible ripples in those fields. When you see an electron, you are not seeing a tiny solid ball. You are seeing a small localized disturbance in the electron field, a small focused stirring of something that fills the universe. When you see a photon, you are not seeing a tiny packet of light traveling alone through space. You are seeing the smallest possible vibration of the electromagnetic field, a small, careful ripple in the same continuous presence that surrounds every magnet and carries every beam of sunlight, from the sun to your kitchen window. Sit with that for a moment, if you would like. Notice how it feels. Notice that it is not really an alarming thing. The world has not changed. The lamp by your bed is still glowing softly. The blanket is still warm. The cup on the nightstand is still cool. None of these familiar things has been taken from you. What has changed, very gently, is the story we are telling about what they are underneath. Underneath the lamp, the photons that carry its light to your eye are not little grains of brightness. They are tiny oscillations of the electromagnetic field, which has been quietly present in the room all along, even when the lamp was off. The field was there. The photons were not. When the lamp came on, the field began to oscillate very rapidly in small, careful portions, and those portions traveled across the room to your eye, where they delivered their small amounts of energy to the cells of your retina, where the field rippled briefly within the chemistry of your seeing. Underneath the blanket, the electrons that hold its atoms together in their long, flexible chains are not little marbles bouncing around in space. They are localized disturbances in the electron field, which is stretched across the whole of the room and the whole of the planet and the whole of the universe. The blanket is, in some sense, a stable pattern in this field. The atoms that make it up are small, stable arrangements of ripples, held together by the soft interactions of one field with another. The pattern is the blanket. The field is what the pattern is made of. Underneath the cup, the same story. Underneath your warm hand resting on the duvet, the same story. Underneath the air between your face and the ceiling, the same story. Every solid thing, every familiar object, every breath you take, every soft sound from the street outside, every photon of moonlight on the floor, every electron in every atom in every cell of your sleepy body is at the deepest level a small focused ripple in a field that stretches everywhere, that fills all of space, that has no edges, that has been quietly present since the first soft moments of the universe. I will say it once more, because it is the kind of idea that benefits from being heard more than once. There are no particles. In the old sense, there are only fields and the small, careful ways the fields ripple. The little grains we thought we were finding when we looked at the world more and more closely turn out, when we look closely enough to be small, focused stirrings of something larger. The bedrock of reality, as far as we can tell, is not made of grains. It is made of soft, continuous fields, varying smoothly across space, capable of vibrating in small, discrete portions. And those small, discrete portions are what we have always been calling particles. Now, I want to pause very gently, because I can imagine how that might land. It is the kind of statement that can sound, said too loudly, like a great unsettling proclamation, as if the world had been pulled out from under you, as if everything was suddenly less real than it had seemed. So let me say, again, that nothing has been pulled out from under you. The blanket is still a blanket. The cup is still a cup. The hand is still a hand. The world is still here. What has shifted is, in some sense, only the words we use to describe what these things are made of at scales so small that no one could ever directly see them. If anything, the new picture is, in its own quiet way, slightly more reassuring than the old one. The old picture said that the world was a great empty void, lightly populated by tiny scattered grains. Most of space in that picture was nothing at all. In the new picture, by contrast, space is full. Not full of stuff in the old sense, not full of marbles, but full of fields, continuous, quiet presences, stretching everywhere. There is no truly empty place. There is no real void. Wherever you look, the fields are there, even if they are doing very little at that particular moment. Even the gap between two atoms, even the deep emptiness between two stars, even the vast distances between galaxies, all of these are filled, in some soft sense, with fields. The universe, in the field picture, is not a thin scattering of grains in an enormous void. It is a continuous fabric with small, careful ripples in it, some of which we have learned to call electrons and photons and many other names. So when you look at your hand in the dim light of the lamp by your bed, you are seeing, in a very real sense, a small, stable pattern of ripples in several overlapping fields. The electron field, the up quark field, the down quark field, the electromagnetic field, all woven together, all humming quietly in the small region of space where your hand happens to be. The pattern has been there since long before you were born, in the form of the particular arrangement of fields that made up the things that became you. The pattern will continue in some form long after you are gone, scattered into other patterns, other arrangements, other small, careful ripples in the same vast, continuous underlying fabric. This is the picture that Paul Dirac, in his quiet way, helped to open. It took many decades to develop fully. It took the careful work of many physicists across the middle of the 20th century to extend the basic idea to all of the known particles and to handle the various difficulties that came with the extension. But the seed of the whole thing was already there in that 1927 paper when Dirac sat with the electromagnetic field and asked very gently what would happen if he applied to it the same small, careful rules that had transformed the inside of the atom. What happened in the end was that the world stopped being made of particles and started being made of fields. Not because anyone wanted it to, not because anyone found the new picture more elegant or more comforting, simply because the equations, when they were written down honestly, came out that way. The universe, on close inspection, behaves like a great soft fabric of overlapping fields, and the small things we keep finding are not the threads of the fabric, but the small, careful trembles that pass through it. So, let us rest here for a moment in this gentle new picture. The room is still the room, the lamp is still the lamp. You are still you, settled in your bed or your sofa, breathing softly, eyes perhaps already half closed. And beneath everything, very quietly, the fields are doing their patient work. The electron field is humming in your hand. The electromagnetic field is carrying the soft light of the lamp to your eye and the warmth of your own body outward into the room. Many other fields we have not yet named, are quietly stretched across the same space, doing their own small, careful work, holding the world together with their soft, continuous presence. We will turn next, when you are ready, to the quiet cast of those other fields, to the gentle inventory of what physics now believes makes up everything. Not a list of particles, although that is how it is usually drawn, but a list of fields, a small, careful family of stretched out, continuous, ever-present underlying presences, the patient ones, the ones that have been here, humming, all along. So let us turn now, very gently, to the small, quiet family of fields that physicists believe are enough, in their patient combinations, to make up everything you have ever touched. This list has a formal name. It is called the Standard Model of Particle Physics. You may have heard the name before. It is usually presented in textbooks and posters as a kind of chart, a tidy little grid of squares, each one labeled with a particle name and a number and a small symbol. The chart is useful. It is a way of keeping track of things. But it is also, in a way, slightly misleading. Because the chart shows particles, and we have just spent the last part of the night gently undoing the idea that particles are the fundamental things. So let us not look at the chart tonight. Let us instead think of the same information, but described in the gentler way the field picture invites, not as a roster of small marbles, but as a quiet inventory of fields, each one stretched across the whole of space, each one present in some small humming way in the room you are sitting in right now, each one capable, when it ripples in its smallest possible way, of producing what we have always called a particular kind of particle. I will go slowly through this list. There is no need to remember any of it. The names will come and go, and they will settle in or they will not, and either way the gentle picture will remain. We are simply walking through a soft introduction, the way you might walk through a quiet room and be shown, one at a time, the small, kind people who have always lived in that room without ever quite making a sound. Let us begin with the electron field. This is, in some ways, the easiest one to start with, because the word electron is already familiar. You have heard of electrons. You have probably been told at some point in school that electrons orbit the nucleus of an atom like tiny moons around a tiny planet. That picture is, as we have already gently seen, not quite right, but it is also not entirely wrong. There really are electrons. They really do, in some sense, surround the nucleus. They are responsible for almost everything that matters about chemistry. They are why the blanket is soft, and the cup is hard, and the metal of the lamp is shiny. The way one electron interacts with another, the way they share and exchange and refuse to share themselves with the electrons in other atoms, is what gives the everyday world almost all of its character. In the field picture, what we are saying is that there is, stretched across all of space, a thing called the electron field. It is here in your room, right now. It is in the air between your face and the lamp. It is inside the pages of any book on your shelf. It is in the cells of your hand and the bones of your wrist and the slow, comfortable warmth of your own breath. It does not do anything dramatic most of the time. It simply rests there like a quiet pond with a value at every point, mostly very close to nothing. But when it is excited in a particular way, when it ripples in its smallest possible configuration, that ripple is what we call an electron. And every electron in every atom of every cell in your body is one of those small, careful stirrings of this single underlying field. The same field, stretched everywhere, always present, sometimes still, sometimes rippling, but always the same continuous underlying thing. If you have ever wondered why every electron in the universe is identical, why each one has exactly the same mass, exactly the same electric charge, exactly the same small set of properties, this is the gentle answer. They are identical because they are all small ripples in the same underlying field. There is only one electron field. The little stirrings it makes, wherever they happen to be in the universe, are all the same kind of stirring, because they are all coming from the same source. There is no difference between an electron in your hand and an electron in a distant galaxy, because both are simply what the electron field does when it is doing the smallest possible amount of something. Now, let us turn very softly to the next field on our quiet list. This is the up quark field. The word quark has a slightly silly sound to it, partly because it was chosen, somewhat playfully, by the physicist Murray Gell-Mann in the 1960s, drawing on a line from a James Joyce novel. The name has stuck, and we have grown used to it, in the way one grows used to any small, unusual word that turns out to be unavoidable. There are several kinds of quarks, in fact 6, but tonight we will focus mostly on the two that matter for ordinary matter, the up quark and the down quark. The up quark field, like the electron field, is everywhere. It fills the room, it fills the air, it fills the inside of every atom in your body. Most of the time, it is doing very little. But when it ripples in its smallest possible way, that ripple is what we have been calling an up quark. The down quark field, similarly, fills everything. Its small ripples are what we have been calling down quarks. And here is where something rather wonderful happens. Because up quarks and down quarks, in particular small careful combinations, are what make up the protons and neutrons inside the nucleus of every atom. A proton, in the old language, is a small heavy particle made of 3 quarks, 2 ups and 1 down. A neutron is similarly a particle made of 3 quarks, 2 downs and 1 up. In the field picture, what we are really saying is that a proton is a small stable arrangement of ripples in the up quark field and the down quark field, bound together in a particular way. The same with a neutron. These are not little hard balls inside the nucleus. They are small, persistent patterns in the underlying fields, gentle little knots held together by something we will come to in a moment. So already, with just 3 fields, the electron field, the up quark field, and the down quark field, we have almost everything we need to make ordinary matter. The blanket, the pillow, the cup, the water in the cup, the walls of your room, the bones of your hand, the cells of your eye. Every solid, familiar thing in your life is, in this picture, made of small, stable arrangements of ripples in these 3 fields. The electrons drift in their patient way around small clusters of protons and neutrons, and the protons and neutrons are themselves small arrangements of quark ripples, and all of it is bound together into the atoms and molecules and tissues that make up the soft texture of your world. 3 fields, then, do most of the work. But of course, the story does not stop there, because for these fields to do anything together, they must communicate. They must, in some sense, talk to each other. They must be able to pull and push, attract and repel, share and bind. And the way they do that in the field picture is through other fields. These are sometimes called the force fields, or, in slightly different language, the gauge fields. They are the fields whose ripples carry the influences that hold matter together and make it behave the way it does. The first of these, and the one we have already met, is the electromagnetic field, the same field that Faraday imagined and Maxwell wrote down in equations, the same field that we spent the last part of the night exploring. It is stretched across all of space. It is in this room with you. Its smallest possible ripples are photons, the tiny portions of light. But the field also does many other things. It is the field that makes electrically charged things attract and repel one another. It is the field that holds the negative electrons in their patient orbits around the positive nuclei of atoms. It is the field that makes the blanket touch your skin without your skin, and the blanket passing through each other, because the electrons in the blanket and the electrons in your skin both push gently against one another through the electromagnetic field. The whole texture of contact, the whole feeling of solidity, the whole experience of touch, is in some sense the work of this one quiet field, doing its soft, continuous work in every part of your daily life. But the electromagnetic field is not the only force field. There are others. They are stranger and less familiar, and they do their work at scales so small that we never directly notice them, but they are no less present for that. Let us walk through them very softly. The next field in our quiet roll call is the gluon field. This is the field that holds the quarks together inside protons and neutrons. The word gluon comes rather charmingly from the word glue, because the small ripples of this field act, in a sense, like the glue that binds the quarks into the small, stable bundles we call protons and neutrons. Without the gluon field, the quarks would not stick together. There would be no protons, no neutrons, no nuclei, no atoms, no ordinary matter at all. The blanket would not exist, the cup would not exist, the hand would not exist. The gluon field is, in its way, the strongest of all the fields. The force it carries between quarks is so strong that quarks, in ordinary conditions, can never be pulled apart. They are bound permanently in the small, careful arrangements that we call protons and neutrons. The gluon field is also a little unusual, in that its ripples interact with each other in a way the photons of the electromagnetic field do not. We will not dwell on the technicalities, but know, in a quiet way, that the gluon field is one of the patient, invisible presences in your room tonight, and that without its soft, strong work, nothing solid could exist. Then there are two more force fields, slightly stranger again, called the W field and the Z field. These two work together, and they are responsible for what is called the weak nuclear force. The weak force is involved in certain kinds of radioactive decay. It is involved in the slow, patient processes by which one kind of particle can quietly turn into another. It is the reason, ultimately, that the sun shines. Deep in the heart of the sun, the weak force allows certain quiet conversions to happen, conversions that release energy and warm the Earth from 93 million miles away. Without the W field and the Z field, the sun would not burn. The light by which you are perhaps reading or listening would not exist. The warm summer days you have known and the soft sunlit kitchens you have stood in would all be impossible. The W and Z fields are stretched, like the others, across all of space. They are in your room, in your hand, in your breath. They do their small, careful work in a way you have never directly felt, but the work matters, and without it, the universe would be a much colder and much darker place. Now we come, gently, to a small group of fields that mostly stay out of the way of ordinary life. These are the fields for the heavier cousins of the electron. There is the muon field. Its small ripples are muons, which are like electrons, but considerably heavier. They are produced when cosmic rays strike the upper atmosphere, and a few of them are passing through your body every second, very softly, without your noticing. There is also the tau field. Its small ripples are tau particles, heavier still than muons, and rarer. These fields fill all of space, just like the others. They are simply less often disturbed in the conditions of ordinary life. And there are the neutrino fields. There are 3 of these, one for each of the 3 kinds of neutrinos. Neutrinos are extraordinarily quiet little ripples. They are produced in great numbers in the nuclear processes of the sun, and they pour through everything, including your body, by the trillions every second, without doing very much at all. They almost never interact with anything. They are, in many ways, the shyest of all the things we know about. Their fields are stretched everywhere, and the small ripples are constantly passing through the world, but you have lived your whole life surrounded by them and inside them, and full of their passing presence, and you have never felt a single one. This is, more or less, the cast of matter fields and force fields, electrons, 3 kinds, and their 3 neutrino partners, 6 kinds of quarks, of which up and down do most of the work, the photon, the gluon, the W and Z. Each one, in the field picture, is a quiet, underlying presence stretched across the whole of space, with small possible ripples that we have learned to call by familiar names. But there is one more field, the newest one in a way, the one that was confirmed most recently, and confirmed at great patient cost by the work of thousands of physicists across decades. This is the Higgs field, and I want to speak about it slowly, because it is, in its own quiet way, a rather lovely member of the family. The Higgs field is unusual in a particular respect. Most of the other fields, when they are doing nothing, when they are at their lowest possible state, have a value of essentially 0 throughout space. The electron field, when undisturbed, sits at 0. The electromagnetic field, when undisturbed, sits at 0. Their resting state is, in a sense, quiet stillness. The Higgs field is different. The Higgs field, even at its lowest possible state, has a value that is not 0. It rests at a soft, non-zero baseline. It is, in every cubic centimeter of the universe, gently present at a small but real value, like the faintest possible glow that never quite goes out. And this small, soft presence does something remarkable. It is what gives many of the other particles their mass. Without the Higgs field present in the universe, electrons would have no mass. Quarks would have no mass. The W and Z would have no mass. Everything would race around at the speed of light, and matter, in any familiar sense, could not exist. The Higgs field is, in a soft, quiet way, what makes it possible for things to slow down, to settle, to gather, to become atoms and molecules and bodies and stars. It is, you might gently say, the field that lets the universe hold still. The idea of the Higgs field was proposed in the 1960s by Peter Higgs, working at the University of Edinburgh, and, at the same time, independently by several other physicists, including Robert Brute and François Englert, working in Belgium. It was a beautiful theoretical proposal, but for decades, no one knew if it was actually true. The way to test it, in principle, was to try to produce a small ripple of the Higgs field itself. The smallest possible ripple of the Higgs field would be what we call the Higgs boson. If the Higgs boson could be produced and detected, then the field must really exist. If it could not, then the theory would be in trouble. To produce a Higgs boson, you have to put a great deal of energy into a very small region of space, energy enough to make the Higgs field ripple in the smallest possible way. This is not easy. It requires accelerating particles to extraordinary speeds, smashing them together and then sifting, very carefully, through the small, confusing aftermath, looking for the rare signature of a Higgs boson appearing briefly and then decaying into other things. This is what was done, eventually, at the Large Hadron Collider, an enormous circular machine, 27 kilometers around, buried gently underground beneath the border of France and Switzerland, at a place called CERN. The work was undertaken by thousands of physicists from many countries, working together patiently over many years. On the 4th of July, 2012, the leaders of two enormous experimental groups, called Atlas and CMS, stood up in a packed auditorium at CERN and announced that they had found, in the data from their detectors, the unmistakable signature of a new particle. Within a few more years of careful study, that particle was confirmed to be the Higgs boson, which meant that the Higgs field, that soft, non-zero presence stretched across the whole of space, was real. It is a quietly moving story when you think about it. A theoretical idea proposed by a small group of patient people in the 1960s. A decades-long search, an enormous machine built by international cooperation. Thousands of scientists working together over years in a careful collective effort to look at something so small and so fleeting that no single human being could ever have hoped to see it alone. And on a particular morning in July 2012, the small, careful evidence finally settled into a clear signal, and the Higgs field was added gently to the inventory of things we believe are really there. So this is the cast, the full quiet family, the electron field, the up quark field, the down quark field, the other 4 quark fields in their slightly less common roles, the muon field, the tau field, the 3 neutrino fields, the electromagnetic field, the gluon field, the W field, the Z field, the Higgs field, about 17 patient presences in all, depending on how you count. It is a small number, in a way, a surprisingly small number, given that this list is meant to compose everything you have ever touched. Every blanket, every cup, every glass of water, every breath, every cell, every flower, every stone, every cloud, every ocean, every star, every distant galaxy, every photon of light that has ever reached your eye, every electron that has ever held a molecule of your body together, every single thing that has ever happened to you in your whole life was the work of small, careful ripples in this small, careful family of underlying fields. That is, I think, a rather lovely thing to settle into. The universe in this picture is not made of countless different kinds of stuff. It is made of a small handful of fields, each one stretched across the whole of space, each one rippling in its own quiet way, and all of them together composing the soft furniture of everything. The chair you may be sitting in, the cup on the nightstand, the blanket, the hand, the slow thought that is forming in your mind as you listen. All of it is the patient work of this small cast of fields doing their small, careful business in the room with you right now. We will turn next, very gently, to the strange and lovely fact that even when these fields are all at their quietest, the universe is not quite still. Even in what we have always called empty space, something soft is happening. But for now, let us simply sit for a little while longer with this small inventory, the quiet cast of fields, the patient family, the soft presences that have been holding the world together quietly all along. So let us turn now, very gently, to one of the quietest and strangest consequences of everything we have walked through so far. It is the kind of idea that, said too loudly, can feel slightly destabilizing. So I would like to say it softly. I would like to say it more than once. I would like to let it arrive in the way late night thoughts arrive, slowly, almost on their own, without anyone making a fuss. The idea is this: if the world is made of fields, and if those fields are stretched across the whole of space, and if even the smallest possible ripple of any one of them is what we have always called a particle, then there is a question, very softly, about what happens when none of the fields are rippling. What happens when there are no particles? What happens, in the most literal sense, in empty space? You might think, at first, that the answer is simple. If no fields are rippling, then nothing is happening. Empty space is empty. There is nothing there. The cup on the nightstand has water in it. The space above the cup, between the rim and the ceiling, has no water in it. The space outside your window, between the glass and the trees, has air in it. The space far above the atmosphere, between the earth and the moon, has very little of anything in it. The deeper into the universe you go, the closer you get to true emptiness. And true emptiness, surely, is just absence. Pure absence. Nothing happening, nothing there. This is what most of us, very naturally, assume. It is what physics itself assumed for most of its history. The vacuum, the truly empty place, was simply absence. The stage on which things happened, but not a thing itself. The dark backdrop, the clean blackboard, whatever you want to call it. The point was that, on its own, it had no content. It was just the space in which content could exist. But the field picture, when you sit with it carefully, does not allow for quite that simple a story. Because the fields, even when nothing is happening in them, are still there. They are still stretched across space. They are still capable of rippling, even if they happen not to be rippling at the moment. They are, in some sense, never absent. And when you bring in the small, careful rules of quantum mechanics, the rules that have been quietly running underneath everything we have said tonight, something rather odd begins to happen. To see why, let us think, very gently, about a simpler quantum object, a small thing called a quantum harmonic oscillator. The name sounds slightly forbidding, but the idea is, in essence, quite domestic. A harmonic oscillator is just anything that can vibrate back and forth in a regular way. A mass on a spring, a pendulum on a clock, a small bell struck softly, ringing back and forth in its quiet little movement. In the classical world, an oscillator can sit perfectly still. You can take a pendulum, gently hold it in place, set it carefully at the bottom of its swing, and leave it there. It will not move. It has no energy. It is, in the most ordinary sense, at rest. In the quantum world, this turns out to be impossible. According to the rules of quantum mechanics, a small oscillator can never be completely still. Even at its lowest possible energy, even when there is no warmth, no push, no disturbance from outside, the oscillator must always have some small residual amount of vibration. It must always be, in some quiet way, slightly trembling. The rules do not allow it to be perfectly motionless. This faint, inescapable trembling has a name. It is called the 0-point motion, and it is, in some sense, the lowest possible amount of motion that a quantum thing can have, which is, very slightly, more than nothing. Now, The connection to fields is this. A quantum field, mathematically speaking, behaves rather like an enormous collection of tiny oscillators, one at every point in space, all coupled together in soft, careful ways. Each one of those tiny oscillators is subject to the same gentle rule. Even at its lowest energy, even when no ripple is passing through, each one must still have a small residual amount of trembling. They cannot all sit perfectly still. The rules do not allow it. What this means when you patiently work through the consequences is that even in what we have been calling empty space, even in the place where no photons are flying and no electrons are passing through and nothing measurable is happening, the fields themselves are still very softly humming. They are not perfectly silent. They are doing the smallest possible amount of something, everywhere, all the time. This is the gentle strangeness at the heart of the night. The vacuum in quantum field theory is not empty. It is the state in which the fields are at their lowest possible energy, but the lowest possible energy is not zero motion. The fields are still doing something. They are still quietly fluctuating in small, invisible ways at every point in space, at every moment. Now, please do not be unsettled by that. I would like to say it again, more softly. The vacuum is the lowest energy state of all the fields. In that state, nothing measurable is happening. No particles are flying anywhere. No light is being given off. No forces are being delivered. From the outside, from the point of view of any ordinary experiment, the vacuum is as quiet and as empty as anything can be. The kitchen at 3 in the morning, when the kettle is cold and the lights are off and there are no people in it, is, by any reasonable measure, empty. The space outside the moon is empty. The space between distant stars is empty. The world, in any everyday sense, has plenty of places that are very nearly nothing at all. But underneath that everyday emptiness, in the soft mathematical language of quantum field theory, the fields are still doing the smallest possible thing. They are humming, very faintly, all of them, at every point in space. They are not flat, they are not still. They are gently restless, in a way that is too small and too quick to ever directly notice. But that is, in some sense, always there. This faint humming has been given a name, or several names. Sometimes it is called vacuum fluctuation. Sometimes it is called zero-point activity. Sometimes, in slightly more lyrical writing, it is described as the way the vacuum quietly breathes. The pictures vary, the mathematics is precise. The point is the same. The deepest possible state of the universe, the state in which nothing is happening, is still not perfectly still. To make this a little more concrete, physicists often describe it in terms of what they call virtual particles. The idea is that, in the soft, restless humming of the vacuum, small pairs of particles can, in some sense, appear and disappear so quickly that nothing measurable is left behind. An electron and its partner, an anti-electron, can flicker into being and vanish again in a tiny fraction of a second. A pair of photons can appear and disappear before any clock could ever measure them. These small fleeting events are not real in the ordinary sense. They cannot be caught. They cannot be put into a box. They do not leave a mark. This image of virtual particles is, in a way, only a metaphor. The mathematics does not really speak of little ghostly particles popping in and out of existence. It speaks of soft fluctuations of the underlying fields, of small humming patterns that come and go too quickly to be called anything as definite as a particle. But the language of virtual particles is sometimes a useful way of pointing at what is happening, a kind of friendly shorthand for a more subtle reality. It is the way we sometimes describe a dream by saying that we were running, when really we were only lying in bed. So picture, if you can, the room you are in. Picture the air between your face and the lamp. Picture the deep emptiness inside the cup of water on the nightstand, if it has been drained. Picture the gentle space between any two molecules of the blanket. In each of those places, in the soft, restless picture of the quantum vacuum, the fields are very faintly humming. The electromagnetic field is fluctuating very slightly. The electron field is fluctuating very slightly. All of the fields are doing the smallest possible amount of something, all the time, in every place. And again, please do not be alarmed. This is not a noisy thing. It is not a buzzing in your ears. It is not anything you can feel. It is happening at scales so small and on time scales so brief that no part of your body could ever notice it. The blanket on your shoulders does not flutter from it. The cup of water does not ripple. The hand resting on the duvet does not shake. The world, in all the ways you actually experience it, is as solid and as settled as ever. The humming is below everything. It is what everything is made of. It does not disturb the room. It is, in some sense, the room. Now, you might reasonably ask, if all of this is too small and too quick to be noticed, how do we know it is really there? How do we know that this is not just a strange feature of the mathematics, a small leftover of the equations, with no real connection to the world? It is a fair question. It is the kind of question I would also ask. And the answer, very gently, is that the soft humming of the vacuum, although it cannot be directly felt, does leave small, careful traces. Small traces that can, with great patience, be detected. And the most famous of these traces has a quiet name. It is called the Casimir effect. The Casimir effect was predicted in 1948 by a Dutch physicist named Hendrik Casimir, who was working in the research laboratories of a large electronics company in the Netherlands. He was a thoughtful, modest man with a quiet mind and a long career, and he was thinking about how the soft humming of the electromagnetic vacuum would behave if you placed something into it that disturbed it just slightly. The setup he imagined was beautifully simple. Take two flat, uncharged metal plates, plain plates, with no electric charge on them, no magnetic field around them, nothing remarkable about them at all. Place them parallel to each other, separated by a small gap. Then bring them very, very close together until the gap between them is extremely tiny, just a few millionths of a meter or even less. In ordinary classical physics, nothing should happen. The plates have no charge. There is no current flowing between them. They are not magnetic. There is, by all classical reasoning, no reason for them to do anything at all. They should simply sit there, two patient plates, separated by their small empty gap. But Casimir worked out, very carefully, what should happen in the language of quantum field theory. The electromagnetic field, even in the empty space between the plates, is gently humming, It is fluctuating in its small, restless way, with all the soft virtual activity that is always present in the vacuum. The presence of the two plates, however, restricts what kinds of fluctuations are possible between them. Only certain kinds of soft humming, certain wavelengths, can fit comfortably in the small gap. Outside the plates, in the wider space around them, the field is free to hum at any wavelength it likes. Inside the gap, the available wavelengths are limited. What Casimir found, with patient calculation, was that this small restriction would have a small consequence. The vacuum between the plates, with its limited set of possible fluctuations, would carry slightly less of a certain quantity than the vacuum outside the plates, with its full, unrestricted set. And this small difference would, in turn, produce a very small but real force pushing the plates gently toward one another. Not because anything had pushed them, not because either plate was attracted to the other in any ordinary way, but because the soft humming of the vacuum was, in a quiet way, slightly stronger outside than between, and the difference would lightly squeeze the plates together. The force he predicted was extremely small, so small that, at the time, no one was sure if it could ever actually be measured. The plates have to be brought extraordinarily close. The experiment has to be extraordinarily careful. Any tiny vibration in the building, any stray electric charge, any small misalignment would overwhelm the effect entirely. For decades, the Casimir prediction sat there, a beautiful small piece of mathematics, undemonstrated in the laboratory. But physicists are patient, and very slowly, over the following decades, the experimental techniques improved. By the late 1990s, careful researchers, including a thoughtful American physicist named Steve Lamoureux, working at the time at the University of Washington and later at Los Alamos National Laboratory, were able to set up experiments delicate enough to actually see the Casimir effect at work. The plates, brought close enough, gently and patiently moved toward each other by exactly the small amount that Casimir had predicted half a century earlier. The vacuum, the supposedly empty space between them, was very softly pushing them together. The soft humming of the quantum field, that strange, unobservable thing, had left a measurable mark on the world. It is, when you sit with it, a rather extraordinary little fact. Two ordinary metal plates with no charge, in the dark, in a quiet laboratory, drifting gently together because of the soft, restless behavior of empty space itself. Nothing was pushing them in any classical sense. No charge, no magnet, no current, no field of force in the old language. Only the vacuum, doing the smallest possible thing all around them, and that smallest possible thing being, very slightly, less in the small gap between them than in the wider space outside. This is one of those moments in physics that I find quietly moving, because what it tells us, very gently, is that the picture we have been walking through tonight is not just a piece of elegant mathematics. The vacuum really is not quite still. Empty space really is not quite empty. The faint humming of the fields really does leave traces, and those traces can be measured, and they come out exactly as the soft equations predict. And again, I want to come back to the room. because it would be easy to let this idea unsettle you, and that is not at all what I would like. So let us return for a moment to where you are. Notice the blanket, notice the pillow, notice the cup, if it is still there. Notice the soft glow of the lamp, or the dim shape of the window, or whatever quiet detail of the room is nearest to you tonight. None of what we have just discussed changes any of this. The blanket is still a blanket. The cup is still a cup. The lamp is still a lamp. The faint humming of the vacuum is not a noise in your room. It is not a vibration you can feel. It is not a disturbance in any ordinary sense in your life. It is, instead, the patient, soft background of everything. It is what the world is doing when it is doing the very least it can do. It has been there since long before you were born. It has been there in every place you have ever sat, every bed you have ever slept in, every kitchen you have ever stood quietly in late at night with a cup of warm something cradled in your hand. You did not feel it then. You do not feel it now. You will not feel it after I have finished speaking. And yet it has been with you the whole time, in every empty corner of every room you have ever been in the gap between any two molecules of any blanket you have ever pulled up to your shoulders. The strangeness, in the end, is also a kind of gentleness. The world is not, as old physics imagined, a thin scattering of tiny things in a great empty void. The world is, in the field picture, a continuous fabric. The fields are everywhere. They never go away. And even in the deepest possible stillness, the smallest possible state, the fabric is not flat. It is very softly textured. It is humming. It is gently restless. It is, in a quiet way, alive. Beneath the ordinary surface of the universe, there may be no perfect silence at all. Only the small patient humming of fields that have been here from the beginning and will be here for as long as there is a here for them to be in. The table is still solid in every way that matters. The blanket is still warm. The hand on the duvet is still your hand, but underneath, in the deepest possible layer, the universe is never quite still and never quite empty, and never quite as alone as it sometimes feels. We will turn next, very gently, to what all of this does to our old idea of solid things, to the blanket, and the cup, and the hand, and the question of what they really are. If everything is fields, and if nothing is ever quite still, and if the small humming we have just sat with is, in some quiet way, part of everything we have ever called real. For now, simply rest. The room is here, the lamp is low, the night is long. And underneath everything, very softly, the vacuum is humming, as it has always been humming, and as it will go on humming, long after this small night and all its small thoughts have been quietly let go. So let us turn now, very gently, to the last part of the night. The hour is late. The room is quiet. The lamp, if it is still on, is doing its small patient work of holding back the dark. The blanket is where it has been. The cup, if there was one, is where it has been. You are where you have been, settled into your own particular corner of your own particular evening, breathing softly, perhaps already half asleep. And the long story we have been telling is coming, very softly, toward its close. Before we let it close, though, I want to do something that, in the spirit of this whole night feels important. I want to acknowledge gently what we do not yet know, because the field picture, beautiful as it is, comforting as it has turned out to be, is not the final word. It is the deepest picture physics has at the moment. It is the picture that the careful work of the 20th century arrived at, and it has been tested in many small, careful ways against the world we live in, and it has, on the whole, passed those tests with a kind of patient grace. The standard model, with its quiet cast of fields, predicts the behaviors of small things to many decimal places of agreement with experiments. The Higgs field, the most recent addition, was found exactly where the equations said it should be. The Casimir effect was measured exactly as the soft humming of the vacuum had predicted. There is a great deal that physics has gotten right in this picture, and there is a great deal of reason to take it seriously. But there is also, very honestly, a great deal that the picture does not yet do, and I think it is worth, at the close of a long night like this one, sitting for a moment with those things, not as a problem, not as a worry, but as a kind of soft acknowledgement that the inquiry is still going on, that the story is not finished, that there are still people, quietly, in offices and notebooks and small chalkboard rooms, trying to figure out what comes next. The most obvious gap, the one that has been hanging quietly over physics for nearly 100 years now, is that the field picture, the picture we have spent the night with, does not yet include gravity. The other forces in the universe, electromagnetism, the strong force, the weak force, have all been folded into the field picture in their soft, careful way. Each one has its own field. Each field has its own small ripples. The bookkeeping works out, and the predictions agree with the experiments, and everything fits together as long as you leave gravity quietly aside. But gravity, the oldest and most familiar of the forces, the one you have felt your whole life as the steady, soft weight of your body against whatever surface is holding you up tonight, has not yet been brought into the field picture in the same way. There is another picture of gravity called general relativity, given to us by Albert Einstein in 1915, and it is also a deeply beautiful picture in its own different language. In general relativity, gravity is not exactly a force at all. It is the gentle curving of space-time itself in the presence of matter and energy. The Earth holds the Moon not by pulling on it in the old sense, but by quietly bending the shape of space and time around itself, so that the Moon, following the straightest possible path through that bent shape, comes round and round again in its patient orbit. This picture too has been tested. It has been tested very carefully over the past century, and it has also, on the whole, passed its tests with grace. The gentle bending of starlight near the Sunday, the slow precession of the orbit of Mercury, the ripples in space-time that we have called gravitational waves, detected for the first time in 2015 by a careful array of instruments, listening for the faintest of stretches in the very fabric of the world. General relativity, in its own quiet way, has done very well. The trouble is that the two pictures, the field picture of quantum mechanics and the curved space-time picture of general relativity, do not yet fit together. Each one works beautifully in its own domain. The field picture works beautifully for very small things. The curved space-time picture works beautifully for very large things. But when you try to apply them to the same situation, when you try to ask what happens at the very heart of a black hole, or in the first impossibly small fraction of a second of the universe's life, the two pictures begin to disagree with each other. The equations stop being able to give clean answers. The mathematics starts to break down gently into infinities and contradictions and small, quiet impossibilities. This means, very softly, that neither picture can be the final story. There must be, somewhere, a deeper description, in which gravity is also part of the quiet, humming family of fields, or in which fields themselves are something different from what we currently think they are, or in which both pictures emerge, in their own ways, from some other underlying thing that we have not yet found. For nearly a century now, patient people have been wandering through this question. They have been doing it in many different ways. None of them, so far, has been confirmed by experiment. None of them, so far, has been ruled out either. They are, all of them, ongoing wanderings in a long inquiry that may take another century, or several centuries, or longer. One of the most well-known of these wanderings is called string theory. The basic idea of string theory is that, beneath even the fields, there is something stranger still. Tiny, one-dimensional vibrating threads, called strings, so small that they are far beyond anything we could ever directly see. Each kind of particle in this picture would be a particular way of vibrating one of these strings. The electron would be one mode of vibration, the photon would be another. Every patient member of our quiet cast of fields would turn out, in this picture, to be a different note played on the same kind of underlying strand. It is a deeply elegant idea, in its way. It has not been confirmed. It may never be confirmed, but it has occupied the careful thinking of a great many people for the past 4 or 5 decades, and it has produced a great deal of beautiful mathematics, and it sits, for now, as one of the gentle possibilities for what might lie beneath. Another wandering is called loop quantum gravity. Here the idea is rather different. In loop quantum gravity, space itself, the very ground on which all the fields are stretched, is not infinitely smooth. It is, at the very smallest scales, made of tiny soft loops, like a great quiet weave. The fields, in this picture, would not be the deepest thing. The weave of space would be deeper. The fields would live on it, like patterns embroidered on a fabric, and the fabric itself, at its smallest scales, would have a small, careful structure of its own. This, too, has not been confirmed. It also may never be, but it has been pursued, with patience, by another community of careful people, for many years. There are other wanderings. There are ideas about emergent space, ideas in which space and time themselves are not fundamental but arise somehow from something deeper. There are ideas about quantum information, in which the soft underlying fabric of the universe is not made of fields at all, but of something more like the patient relationships between very small bits of information. There are many other small, careful programs, each of them being walked through by thoughtful people, each of them offering a different, gentle guess about what might lie beneath the field picture we have spent the night with. None of these is in competition with the others, really. They are different paths up the same patient mountain. They are different small candles being held up in the same long, dark room. Whichever of them turns out to be on the right track, or whether all of them are pointing towards something that none of them has fully grasped yet, The inquiry itself is ongoing and quiet and rather lovely and not finished. What I would like you to take from this, if anything, is something very soft. The field picture is the best picture we currently have. It is deep and beautiful, and it agrees with the world in many small, careful ways. It is also, almost certainly, not the final picture. There is something beneath the fields, or beside them, or around them, that we have not yet quite seen. Physics is still wandering. It is still patient. It is still, in its own quiet way, finding small new things in small new corners. I find this, late at night, rather comforting. It means that the universe is not yet fully explained. It means that there is still wonder available, still mystery, still the soft possibility that something deeper is waiting to be found. The blanket on your shoulders, the cup on the nightstand, the lamp by your bed are not just made of fields. They are, in some sense, made of something we do not yet fully understand. And that is all right. That is, in some way, the gentlest part of all of this. That even the people who have spent their entire lives thinking about these things do not yet quite know what they are. They have come to a deep and patient picture. They are still looking. They will go on looking long after this night is over. Now let us come back, very softly, to where we began. To the room, to the small, ordinary things. Notice, if you would like, the weight of whatever is covering you tonight. The blanket, the duvet, the coat, the soft heaviness of whatever has been keeping you warm through this long, quiet evening. Feel it pressing gently against your shoulders, your chest, your legs. It has been there the whole time. It has been holding you quietly while we have been wandering together through fields and ripples and humming vacuums and unanswered questions. The blanket in the deepest picture is a meeting place of fields. The electron field in the patient cells of its fibers, the up quark field and the down quark field in the nuclei of every atom in every thread, the electromagnetic field holding the whole soft structure together, carrying the small soft messages between one molecule and the next, the gluon field in the bound bundles of quarks at the very heart of every speck of matter in the blanket, the Higgs field gently giving everything its mass so that the blanket can have weight and warmth and presence at all. The blanket is, in some sense, a small quiet place where all of these fields have settled into a familiar pattern, a particular soft arrangement, a particular way of overlapping, of humming together, of refusing to pass through one another, of holding their shape. Underneath the simple, soft warmth of it, the universe is doing a great many quiet, careful things at once, and the result, the gentle outcome of all that small, careful work, is the warm blanket on your shoulders. Notice the pillow under your head. The same story. A particular meeting of fields, a particular soft arrangement of patient overlapping ripples. The shape of it, the give of it, the way it has curved itself gently around the shape of your skull. All of it is the outcome of the quiet, humming work of the underlying fabric of reality. The pillow is a small place where the universe has settled into a particular familiar pattern. It is, in its own small, soft way, a meeting place. Notice the glass on the nightstand, if it is still there. The cool of it, the smooth rim, the water inside it, still and clear. The same story. a quiet pattern, a particular meeting of fields. The water is a soft, careful arrangement of patient ripples in many of the same underlying presences that make up the blanket and the pillow and your hand. The glass is another. The room is woven through and through with the same continuous quiet fabric, doing different things in different small regions, each region producing one of the small, ordinary objects that make up the soft evening of your life. Notice your own hand wherever it is. Your hand is a meeting place too, a particular pattern of ripples in the same underlying fields that make up everything else. Your skin, your fingers, the slow, steady warmth of your blood beneath the surface, the small, patient cells, the long, careful molecules, the atoms, the quiet electrons, the deep quark bundles in every nucleus. All of it is the work of the same humming family. Your hand is, in this picture, a small piece of the soft underlying fabric of the universe, gently doing the particular thing that it has been doing since you were born. You are not separate from the rest of it. You are made of the same quiet stuff. You are a small, soft part of the same patient humming. This, I think, is the gentlest thought I can leave you with tonight. The hand on the blanket, the head on the pillow, the eyes that may already be closed, the slow, steady breath in your chest, the small, private thoughts moving softly through your mind. All of these are part of the same continuous fabric that is doing its quiet work in every other corner of the universe. Every star, every distant galaxy, every small soft cloud of gas drifting between galaxies, every patient photon traveling for billions of years across the dark, every small humming corner of the vacuum in every empty place in the cosmos, all of it is the same fabric. All of it is the same family of fields. And you lying in your bed, in your quiet room, on this small, soft planet, are made of exactly the same fabric, woven through with the same fields, hummed into being by the same patient, quiet activity that holds the rest of it together. There is something, I think, gently comforting about that. It is the kind of thought that makes the world feel a little less lonely. The blanket on your shoulders is not a separate thing pressing against a separate you. The two of you are the same soft fabric, gently overlapping. The room around you is not an alien space. It is the same fabric in slightly different patterns. The night sky, when you cannot see it tonight, is not a distant, unrelated thing. It is the same fabric, stretched a great deal further. The light from the most distant stars, when it eventually reaches the small atmosphere of this planet, is just the same patient electromagnetic field doing what it has been doing in your bedroom all evening, only with a longer journey behind it. You are, in some quiet sense, woven from the same soft fabric as everything else. The strangeness of that, when you let it settle, is also a kind of belonging. You are not separate from the universe. You never have been. You are a particular small pattern in it, a particular meeting place of fields, a particular humming corner of the same quiet activity that is going on everywhere. The universe, on this small night, has settled into the particular shape of you, lying in your bed, listening softly to a long, quiet voice in the dark. So let us let the night close, very gently, without conclusion, without summary, without anything sharp or final. Let the long story rest where it is. Let the fields go on humming, as they have been humming all along. Let the blanket be a blanket. Let the cup be a cup. Let the hand be your hand. Let the room be your room. Let the strangeness, when it comes to you in the soft, quiet moments before sleep, be gentle. Let the picture of the underlying fabric, when it returns to you in the small, quiet moments of tomorrow and the days after, be a kind of soft companion rather than an unsettling thought. There is a hum beneath everything. There has always been. There will always be. It does not ask anything of you. It does not need to be understood. It is simply there, the way the sky is there, the way the ground is there, the way the soft weight of your own body is there as you settle deeper into the bed tonight. The hum is the patient music of the world. It has been here from the very beginning. It will go on long after this night and all its small thoughts have been quietly let go. So drift when you are ready. Let your eyes close, if they have not already. Let the small, soft thoughts of the night settle into wherever they want to settle. Let the long, quiet story we have walked through together come gently to rest, like a book closing softly on a side table. The blanket is still warm, the pillow is still soft. The lamp, if it is still on, can be turned off whenever you like, by whichever quiet hand is willing to reach for it. And beneath everything, in the soft layered fabric of the world, something is humming. It has been humming all along. It has been humming through every blanket you have ever pulled up to your shoulders, every cup you have ever held, every hand you have ever taken into your own. It will go on humming, very gently, while you sleep. It will go on humming tomorrow when you wake. It will go on humming for as long as there is a universe for it to hum in. And you are, in your own small, soft way, a part of that humming. You always have been. You always will be. Good night. Sleep softly. The universe is humming, very quietly, just beneath the surface of your room. It is glad you are here. It will be glad when you wake again. It has been holding you in its patient, soft way all along.